In order to demonstrate the general enhancements made to Lattice, we will be using a model of a hip implant. We will be adding some Lattice for mixed reasons, such as making the implant lighter and at the same time reduce material. We will also add some Lattice to fixate a joint surface layer of polyethylene to the implant. To access Lattice in NX, there are a few entry points. If in modeling environment and with the correct licensing, you can access it via Menu, Insert, Design Feature, and Lattice. Lattice is also accessible via the Design for Additive Manufacturing tab on the ribbon bar if activated. Here I have the Lattice group added to my Home tab for easy access. Zooming into the area we want to modify, we turn on the sectioning to show all the parts of the implant. The sectioning also reveals a cavity inside the implant, here represented by the beige part. It is this cavity volume that we will use for our initial lattice. We also note that the cavity is not quite following the exterior shape, and there is a reason for that we will look into in more detail later on. So let's get started in creating our first lattice. We start the lattice application. A tip here is to turn off the preview, as this can cause some weighting depending on the complexity of your lattice, shape of the fill volume or surface, and what settings you are using. As we want to fill a volume with a specific lattice, we set the lattice type to unit fill and select the already prepared cavity volume. We notice that for this version of NX, we have added information such as stiffness and porosity to the existing unit cell library. However, here we have prepared a custom defined cell type to fit our specific purpose. We therefore choose to define the unit cell from File and navigate to the location of our custom lattice type library and select the required definition file. With the volume to fill defined and the lattice cell type defined, we notice in the lower right corner that the system returns feedback and warns that the rod size is in violation to the cell size and that the result would most likely be undesired. We therefore modify the cell size to something more suitable, and we modify the rod size as well. The small cell preview in the middle of the volume in the graphical screen gives us an indicator to what the lattice pattern will be like. Reviewing the lattice by using Show Result, we see that the lattice is somewhat poking through the volume defining it. Should this be undesired, this version of NX now offers the capability to limit the lattice to the boundary volume by using the option Snip at Boundary. As usual, we execute the preview and review the lattice fill level of the defining volume. As the result is up to our requirements, we confirm and accept the lattice creation. We review the resulting lattice and notice that there are dangling bits. While in creation mode of the lattice, there are options to remove the dangling bits. In addition, you can also filter the lattice and create a filtered lattice with the requirements you desire. Here we choose to filter the first level, where NX filters rods not connected in both ends iteratively until it hits the first manifold vertex. Note that the filter creates an additional feature containing the filtered geometry. We can hide and show the original lattice and the filtered version of the lattice to see if it is what we require. In this case, we undo the result as we want the lattice to actually be part of the implant and therefore be limited by the volume defining it. We will now continue by adding the fixating mesh to the implant's ball joint. To make it clear, we hide the socket attaching to the hip. The intention here is to add a mesh to the ball of the implant, as this will help fixate the polymeric layer of the ball. As the mesh we require does not exist, we need to create it. The process to create your own lattice cell unit is extremely simple. Here we have made it even easier by using an existing part containing curves to define the custom lattice cell unit. In the part, the defining curves have been created inside a cube 100 by 100 by 100. By utilizing the unit cell editor and setting the filter to select curves only, we quickly define the custom cell unit. A tip here is to keep the number of segments to a minimum. Depending on the complexity of the lattice unit cell or the curves defining it, you might want to use more segments for accuracy. However, you should be aware that it will impact the performance, so please be careful when you set the number of segments here. We save the cell unit to required location for later reuse defining our custom lattice. With the custom lattice unit cell defined, we return to the implant to actually add it as a lattice to the ball of the implant. Hiding the polymeric layer of the ball, that is to be fixated to the lattice, expose the ball surface to use as base for the mesh fixating the polymeric layer to the ball. With the surface we intend to use as base for our lattice exposed, we again evoke the lattice function. We change the lattice type to unit conformal, which will create a lattice pattern where all the angles strive to be equal. This will create a perfect lattice for our purposes. We navigate to and select our just custom-made cell type. As this mesh is created to firmly fixate the polymeric layer to the ball, and since the polymeric layer is rather thin, we toggle off the uniform cube option and set the size to our requirements. We also reduce the rod size before accepting the result. Should this lattice have been the reinforcement of, let's say, an entire polymeric design, we might want the two lattices connected. In order to do that, the core lattice would then, however, most likely have been following the outer shape. This can easily be fixed with this release of NX, as lattice now is an associative feature. To demonstrate, we will change the inner volume defining our first lattice. By redirecting the associative extract feature defining the volume boundary of our lattice and pointing it to the already prepared volume associatively following the outer shape of the implant, we show that the lattice from this release of NX is an associative feature. Really good news for automating all the customer processes out there. As the inner and outer lattices now follow each other in the ball area where we intend to connect them, we have a great setup for to use connect lattices. We select the two lattices to be connected and set the appropriate parameters in the feature menu. Increasing the checking distance here would of course increase the number of connection points between the lattices. Adjust the checking distance value to best fit your purpose. We also note that we receive a warning that not all bodies can be connected. That is due to the dangling bits we chose to keep earlier. Note that the resulting connected lattices feature also produces its own resulting body, just like filter lattice earlier. Reviewing the connected lattice together with the implant shows that it would work perfectly should the implant be polymeric and not hollow. However, since the lattice structure is intended to lightweight the metal implant and be merged with the same, the connections between them are not needed, and therefore we return to the previous state by undo. Finally, in this demonstration, we will add a lattice to the implant that will help fixating the joint or seam area between the implant and the polymeric surface. Doing so, we will see that the randomize option have been improved, and from this version of NX do not extend outside the fill volume. We once again evoke the lattice function and change the lattice type to something more suitable. Here we will use the quad diametral line option. We also change to utilize the uniform cube definition. As the edge length is way high in relation to the size of the fill volume, we reduce the edge length to 1. With the edge length set to 1, the rod diameter also must be reduced to obtain a good lattice. The preview provides a good overview of the results, and we see that the required lattice pattern is shown. By turning on randomized graph nodes, we assess if the provided result is a good lattice for the fixation purpose. The randomization takes place inside the volume. However, the lattice nodes might appear outside as it is the last vertex in the volume. By using lock boundary, you can exclude the randomization near the boundary where you will get a normal pattern of your lattice. Inside the randomization will be executed as per requested if the volume is big enough. In this example, the volume is very small and the randomization is very limited with this option. As the regular pattern in our example is better fit for our solution, we turn the randomization off and accept the result. With all the lattices required created, we tidy the model by showing all the lattices that have been hidden. We also show the polymeric surface fixated by the lattice on the ball, as we might want the empty space within the lattice structure to be filled, preventing human tissue to get inside. We also bring back the fill volume and make it translucent to show the lattice. This concludes the demonstration on the really great enhancements to Lattice implemented in this release of NX.